Hi, Eric. Hi, Jimmy. Can you hear us?
Can you hear me now?
Yes, I can hear you. Can you hear
Good.
us?
Yep, just fine.
Ah, perfect. Eric, can you hear us too? Mhm.
All right. Can you hear me?
Yes, can hear you. Can you hear us?
Yes.
Awesome, awesome. We were in a new room, so we're kind of figuring it out, but okay, sounds good. How are you doing?
Doing really well. How about you guys?
Good, good. We're ready to present, show you our work for this year, and yeah, we're excited.
Sounds fantastic. Let me pull up notes here. All right. So I saw, yeah, I can see that we're recording, so that's good. What's your guys' team number?
We're Team 116 from the University of Florida.
16. Okay. 4-29. All right. Let's go ahead and get started.
Cool. So yeah, we have about an hour presentation for you, and then we also have it open for some questions at the end, if that works out.
Yeah, that's fine.
All right, sounds good. So if you're ready, we can go ahead and get started. All right, cool. Hi, everyone. Thanks for joining today. I'm Maya Green. I'm the project manager for this year for our Spaceport team. Our project name for this year is He's Right Behind Me, Isn't He? And I mentioned we're Team 116, Swamp Launch Rocket Team from the University of Florida. It'll let me switch. Okay, there we go. Cool. So this is our team. We're competing for the second time in the Spaceport America Cup this summer. So last year we competed in the 10K COTS category, and we're competing in 10K COTS again. And so you can see us here with our rocket. We have a horror theme going on in the back. And yeah, so we're really excited to attend again this year. So about our team structure a little bit, I'm the administrative manager of the team. So I'm the direct line of contact between our executive board and our technical team. And our technical team is led by our technical manager, the chief engineer, who oversees all of that technical development that we do throughout the year. We also have our vehicle integration engineer that oversees the avionics and recovery, composites, structures, and flight dynamics subteams, and our payload integration engineer that oversees the electrical, mechanical, software components of our payload. This year, we've also come up with a new initiative, which are our development teams. So this year we have 3 development teams that are controls, propulsion R&D, and propulsion manufacturing. These started out as projects that were meant to have a longer timeline of at least 2 years or so. And so we have our controls development team that's working on an air brake, and they've actually made enough progress to include on our competition rocket this year. So we're really excited about that. In terms of our propulsion R&D, we're working towards creating our own propellant so we can join the SRAD category in future years. So we're still working towards that goal, hopefully in the next couple years or so. And we have propulsion manufacturing, who had the main goal of this year of developing a test stand for us to start doing some static fire testing and pressure testing.
Hi, everyone. My name is Megan Winek, and I am the chief engineer for our project this year. So as Maya indicated, I'm the technical manager of the project. I'm going to give a broad kind of overview of our project before handing it off to our technical leads to do most of the talking. But just to give a little bit of status on our project, we are on track with the competition to attend in June. We've submitted all of our documentation on time as well as paid our fees. We've also completed a fully integrated test flight of our entire project. And we're currently, this was largely successful. So we're currently just wrapping up a few mitigations and fixes that we needed to make following that test flight. And we are slated to be doing our final testing in the next just like few days to be ready for the rest of the summer. All right, so to introduce our project, as Maya said, the overall title of our project, as well as our launch vehicle, is He's Right Behind Me, Isn't He? And we have a little bit of a theme from The Shining going on. Our payload's name is Here's Johnny, and the payload is a deployable chase camera. And so that's where the name came from. The payload is going to essentially follow the rocket and chase it upon descent. So that's where He's Right Behind Me, Isn't He? Came from. And then along with that, we also have, as Maya mentioned, our SRAD air brake, which one of our development teams was working on this year. And again, this was a really successful project, and we flew this on our test flight, and we also are going to be flying it in competition as well.
Hello, everyone. My name is Kaan Aslan. I'm the launch vehicle integration engineer, and I'll be giving a quick overview of our launch vehicle and our mission profile before it leads. So our launch vehicle stands at 165 inches tall, has an outer diameter of 6.14 inches, and has a liftoff weight of 95 pounds. Our target apogee is 10,000 feet, and our choice of motor for this mission is a Aerotech N3300 RPS motor, which has a total impulse of 3,015 pounds. And we have a dual deploy recovery mission where we have a drogue parachute that deploys at apogee, and we have a main parachute that deploys at a lower altitude. However, on top of this, we have a third separation that happens to deploy our payload, which makes it so that we have 3 events that happen during flight. And our airframes we have a payload airframe, we have a main airframe, a drogue airframe, and an aft airframe, which are joint with 2 avionics bays and our air brake systems coupler. So for the connection points, we have our payload that sits inside the payload airframe, and the nose cone connects to the payload airframe, creating our first separation point. And we use metal rivets to create our non-sliding rigid joints. And we have our main parachute that's inside the main airframe that connects to the forward avionics bay with shear pins, creating our second separation point. And we have our drogue parachute sitting inside the drogue airframe that connects to our second avionics bay with shear pins, creating our third separation point. And our drogue airframe connects to the aft airframe with the help of our air brake coupler, and it's secured from both sides with metal rivets to create a non-separating point.
So hey everyone, I'm Jose Chavez. I'm this year's Spaceport Composites lead. So I'll quickly go over all the aerostructure components and what they're made of. So we have our nose cone, which is SRAD fiberglass reinforced plastic. Our payload airframe and our main airframe are COTS G12 fiberglass, and our drogue airframe, motor airframe, and our fins are carbon fiber reinforced plastic, SRAD carbon fiber reinforced plastic. Our airframes are manufactured with using a 6-inch polycarbonate mandrel. They're made with carbon fiber sleeves, and they're 3-ply symmetric layup. The first ply is a 12K unidirectional carbon fiber sleeve, and this is sandwiched between 2 by 3K biaxial sleeves. It is always good practice to actually compress your part when you're carrying your composite. So we do this by wrapping PET flash tape around in a helical pattern, and this is able to achieve a greater fiber volume fraction and therefore a greater strength in our part. So our airframes were tested using compression testing, doing a displacement control test. We did our compression testing with applying load using a thrust ring, which would be how it's actually in flight, how the load would actually be transferred to the airframe in flight, and then also an aluminum plate for the other side to distribute the load and also protect the machine. We had 2 test sections. One was with and one was without flaps cut out. These flaps cut out, I'm not sure if you can see this, but we have flaps cut out in our aft airframe. 2 of them. This is where the air brake flaps will be actuated. So this will create a huge stress concentration. That's why we wanted to include that in our testing. So as you can see, our max load for a flap cutout was around 7,500 pounds. We designed for a factor of safety of 3, and we achieved the margin of safety of 0.39. So here is our fiberglass nose cone. We chose fiberglass for its lightweight, its strength, and its radial transparency. It was made using a Bunkarman 4:1 PLA mold, and we used 5 layers of 3K fiberglass E-glass bidirectional sleeves, wetted out with solar composite 820 epoxy system. This was compressed using a vacuum bag, and for post-processing, we used Bondo to fill all the pinholes and sanded it to achieve a smooth surface. Our nose cone here at the top, it was made out of 6061 aluminum and also made using the Haas SL10 CNC lathe. Our carbon fiber fins, it's made using prepreg. They're right here with the aft. We use a Torre T300 250F epoxy standard prepreg. That is our laminate code right there. And it is about an average thickness of around 180 thou. Using prepreg, you can achieve a really high fiber volume fraction, around 60%. We manufacture this on an aluminum tooling plate and put Teflon, then our plies, and then Teflon again. This is to Teflon was used just to demold the actual part so it wouldn't stick to the aluminum plate, and also just apply a smooth surface on the top and bottom. And this was cured, vacuum bagged, and cured in a temperature controlled oven. All the fins were cut on a 5-axis abrasive water jet cutter. So we also wanted to find the effective laminate engineering constants of our actual fins. In order to do this, we need to find the actual engineering constants of our material itself. So just the one ply of prepreg. We did this by using digital image correlation testing. We had a 12-ply 090 laminate. It was around 120 thou thick. We speckled it with a white spray paint just to apply a good first base coat, and then we actually speckled it with black, so that way the digital image correlation can detect the strains. We ran like a coupled UTM and digital image correlation systems that record data at a frequency of 2 Hertz. So for our touchstone testing, we followed ASTM D3039 standards. For our shear testing, it was done using shear testing procedures that were developed in the UF's composites lab. For our extensional modulus in the fiber direction, we achieve a extensional modulus in the fiber direction of 53.681 gigapascals with Poisson's ratio of 0.249 and the in-plane shear modulus of 5.287 gigapascals.
Hi, my name is George Issa. I'm the structural design lead for the team this year. And one of the major projects that's being done on the launch vehicle this year is the design analysis manufacturing of a modular aft. It's important to consider some of the disadvantages of a more traditional epoxy aft that's used on a rocket. The main disadvantages would be the cure time that's taken in order to produce an actual epoxy aft, which would increase the manufacturing and assembly time. Additionally, cutouts must be made into the airframe during the assembly process, which would sacrifice the structural integrity of the airframe. And the aim of modular aft section is to mitigate some of those disadvantages. So here's the design that we ended up going for. It consists of 4 centering rings that aim to center the motor and make sure any thrust transmitted by the motor is transmitted axially into the rocket. They're connected using a set of aluminum standoffs. And the main purpose of that is to ease the assembly process in which all of the centering rings can be assembled and then inserted into the actual airframe to finalize the assembly process. Another aspect of the design is the fin brackets, which you can see right here. They sit outside the airframe and fasten into the centering rings using radial holes that are drilled into the side of the centering rings. And then finally, a thrust plate was designed and connects to the bottom of the bottommost centering ring. This is the main attachment point of the motor, in which the motor retainer screws onto the bottom of the thrust plate. Additionally, it has a shoulder that sits outside the airframe in order to better translate any loading caused by the motor during flight. So the manufacturing process this year was aimed to be fully automated, in which the multiple parts could be manufactured to the desired specifications and tolerances. This was done using 3-axis CNC milling, 4-axis CNC milling, and abrasive water jet cutting. As you can see in the picture in the middle, the fin brackets were machined out of a 1x1 inch bar stock of aluminum 6061 on a 3-axis CNC. The centering rings and thrust plate were cut using an abrasive water jet on a 1/4 inch and 1/2 inch sheet of aluminum 6061, and then any radial holes were drilled on the 4th axis of the CNC. Another major component of the design is the derivation of our load case, which is used to simulate any loading caused during flight. This consisted of 3 main loads, the first of which being the thrust exerted by the motor on the assembly, and was found by taking the maximum thrust exerted from the motor through the thrust curve. The second major force is the inertial force, and is not an actual force applied during flight, but is a way to convert the dynamic model of the rocket into a static one that could be more easily simulated. This was found by taking the maximum acceleration of the rocket and multiplying it by the initial mass. The final force applied on the actual aft section is the drag caused during flight. This was split into 2 main components, in which one was applied directly onto the tip of the fin going this way, and the other was applied on the side of the fin during flight. The first component of the drag was found using a high drag coefficient in order to ensure that any drag caused during flight would not exceed the simulated drag. The second component was found by finding the drag coefficient correlated to the highest angle of attack using an open rocket simulation. This was found to be 5 degrees, and the side drag was found based off of that. Additionally, fastener analysis was conducted in order to ensure any loading caused during flight would not result in failure of any fasteners. This was done by using the equation you see here, where the stress caused by any loading resulting on the fastener is compared to the ultimate tensile strength or the ultimate shear strength of the fastener, and N is the number of screws in order to achieve a high enough area to decrease that stress and ensure it's under the ultimate tensile strength. The shear yield strength was taken to be about 50% of the ultimate tensile strength, and the result of this equation is us ending up selecting 632 fasteners for the top 3 centering rings, 1024 for the bottom ring, and then 1/4-20 fasteners for the thrust plate. So once the fastener analysis was conducted, a static structural study was done on ANSYS Mechanical in order to ensure that any loading caused during flight wouldn't cause failure to the modular aft section. As you can see on the picture on the right, a support was fixed on the outer shoulder of the thrust plate. This was done to ensure that any loading applied during the simulation would not be directly applied on the support, and the results could be actually accurate in the sim. Additionally, frictionless supports were applied on the fin brackets, mainly on the faces that interact with the airframe. Since there's no airframe in the actual study, a frictionless support had to be inserted in order to account for that. And then 1/2 of the actual modular aft design was selected for the simulation. This was done so in order to decrease any computational time while maintaining relatively accurate results. This also meant that any forces derived before had to be divided by 2. As for the distribution of the inertial load, it was treated similar to the distribution of stress onto the thread of a fastener. This was mainly done because of the nonlinear weight distribution of the rocket above each centering ring, and therefore the picture on the left shows you that distribution, where 38% of the inertial load is exerted on the top ring, 27 on the second to top, 20 on the third, and then 15 on the bottom. Finally, any bending stresses calculated before from the drag were directly applied onto the side of the fin brackets, and bolt pretension was applied in order to ensure that any torquing was accounted for during the simulation. Initially, the design was simulated without any weight-saving cutouts in it. This was mainly done to observe any regions that exhibited high stress, and this was found to be the regions of the centering rings around the radial screws. And then an iterative design approach was taken in which weight-saving cutouts were conducted, and then a new simulation was assembled and the stresses were observed. This was done multiple times until a desired safety factor was achieved and the overall design was light enough. As you can see here, this is the final form of our simulation. The maximum calculated von Mises stress is 26.3 KSI, which is well below the ultimate tensile strength of aluminum 6061. And the target safety factor was 1.1, and we achieved a margin of safety of 0.21. And then finally, the total mass of the system was found to be 95.2 ounces.
Hello, everyone. My name is Jacob Burdick, and I'm this year's avionics and recovery lead. And with my main job of making sure the rocket comes down safely, that's mainly achieved through the timely ejection of our parachutes. And housing the avionics that control those ejection timings, we have this here, which has three main components: the couplers, switch bands, and bulkheads. And those couplers are made of G12 fiberglass and they're cots. They're 13 inches in length, with one of those inches being contributed to with the switch bands, allowing 6 inches on either side to insert into both sliding and non-sliding joints. And to secure those joints, we use 3 metal rivets for the non-sliding joints and 4 plastic shear pins for the sliding joints. Our switch band is SRAD carbon fiber reinforced plastic, which was manufactured through our own layups and dremeled off of the airframes. This switch band has 4 altimeter pressure ports, which were sized based off of the altimeter manufacturer recommendations. We have bulkheads on either side to seal it off, and those are both made of aluminum and steel, and those are 1/2 inch thick, and they were water jet and then CNC milled to have a 1/4 inch shoulder, and they were pocketed down to 1/8 inch with analysis based off of the inertial loading of the rocket during ascent. And the reason we have both aluminum and steel bulkheads is to allow for this top plate to be swapped out to alter the weight of the rocket. And this is to account for the change in altitude as we go from Florida for our test launch to New Mexico for our competition flight. And moving on to the avionics that are housed in those avionics bays, we have our SRAD flight computer, which this year will only be data logging. And we have 4 COTS altimeters. Additionally, we have a tele GPS, which is housed in the nose cone in this coupler here. And that is fastened onto a PVC bulkhead, which was epoxied in. And that tele GPS is then fastened onto that bulkhead using a 3D printed bulkhead also. Our 4 COTS altimeters are a Stratologger CF, 2 MissileWork RRC3, and a Blue Raven. And our aft avionics bay is the avionics bay that controls both our drogue and main parachute deployment. And that primary altimeter will be the Stratologger CF, which means the drogue channel fires at apogee, with our main channel firing at 1,000 feet. The backup is the RC3, which fires at the drogue channel at apogee plus 2 seconds, and the main channel at 800 feet. Our forward avionics bay controls the payload deployment, and with that, the RC3 is the primary altimeter, which means it does not have to fire anything at drogue, and on the main channel fires at 1,250 feet. The Blue Raven is then the backup and fires at 1,100 feet. More on our SRAD flight computer, the electronic components we chose were the Arduino Nano, BMP390, MPU 6050, and SD card module. One thing to note is that the MPU 6050 will no longer be included, and we encountered stability issues as we ran the code, and after 60 seconds, it would then stop running. The only case we used the MPU 6050 was for launch detection, and this was to allow for redundant detection, accounting for both the altitude change based on the BMP 390 and acceleration detected by the MPU 6050. This was then changed to only account for a altitude change used by the BMP 390 with an altitude arming altitude. So more on that software logic, we have our setup, and this setup accounts for the altitude and takes the mean, and then it will then offset the following altitudes based off that mean, and this is to then read out above ground level altitude. Upon this, we then begin looking for launch detection, and launch detection again is detected through a arming altitude, and this takes the last 20 samples of data, which we're sampling at 20 hertz. So the last second of data, and if all of those readings are above the altitude of 300 feet, we have then detected launch. And once we detect launch, we then have an offset of 5 seconds, and this is to account for motor burn and that acceleration in order to not have any false detections of apogee. As we pass that 5 seconds, we then begin look for a decrease in altitude, which would then be apogee. Following that, we then look for our main altitude, which is a preset parameter based off of what we choose. And for this, it will be housed in the forward avionics bay, which controls payload deployment. So this was set to 1,250 feet, simulating it acting as the primary altimeter. This was flown on our test flight and was successful and staged at all the correct components or at all the correct timings. We also have a SRAD CO2 system, and this is to deploy our payload. And the reason we use this is it uses cold gas and has no ejection residue. And this is really important compared to black powder, which we use for both main and drogue deployment, as it does not pose a risk to any of the precious electronics on the payload and ensures that its mission is safe and there's no risk of it from the ejection of the system. And the mechanism that controls this is we use a small amount of black powder to propel the puncture piston into the seal of the CO2 canister. And upon this seal breaking, the return spring then brings the puncture piston back to the top position, and this allows the gas to escape. And it travels through the relief holes on the canister mount and into the airframe, pressurizing it and allowing the nose cone to come off, as well as the payload. This was mainly manufactured using a lathe and we used a mill to drill out any of the non-concentric holes. Based off of the spring constant of the return spring, this is rated for 200 plus Gs, and this accounts for the acceleration loadings of the puncture piston prematurely puncturing the CO2 canister. And our recovery layout follows a sequence of eye bolts, D-links, shock cord, and swivels to connect our avionics bays, our parachutes, and our payload sabot. And we follow a dual deployment recovery method where we have a drogue parachute, which aims to reduce drift and controls the maximum deployment force of the main parachute, with that main parachute controlling the ground hit velocity. This year, we used 2 drogues. The 3-foot standard with a coefficient of drag of 0.97 was used in Florida for our test flight, and that brought a descent rate of 106.6. However, with this fast descent rate, we experienced severe zippering of our main parachute, which then leads us to use a 3-foot elliptical with a coefficient of drag of 1.6, bring our descent rate to 83 feet per second to reduce that risk of zippering. Our main parachute is going to remain the same as what we used for our test flight, which was a 10-foot Ars Ultra 2.2 coefficient of drag parachute, which brings our main ground hit velocity to 19.2 feet per second. Some more on that recovery force that we experience. This is experienced from the main parachute deploying at drogue velocity. And to account for the fill time of our main parachute, we have a shock factor of 0.9, which was gathered from OS Calc to account for this fill time again. Based off of this loading, we then include a safety factor of 1.5 to bring our design force to 3,000 pounds of force upon main deployment. And to distribute this loading into the rocket and all the eye bolts and D-links, we then assume the rocket accelerates uniformly from this force. So any of the weights that are being held by this component can then be multiplied times acceleration to find this force. And using this force, that means our minimum factor of safety is 1.5 for all of these components. Additionally, our shock cord is rated for 6,000 pounds, and this is to account for any of the knots that are needed to tie that would reduce this strength.
Hi, everyone. I'm Joseph Pinkson. I'm the controls development lead for the team this year. Our objective for the year was to design and test a variable drag air brake system that will allow our launch vehicle to reach within 1% of our target apogee, which is 10,000 feet for this year. The working principle for our air brake system is through deployment of radial flaps, as seen in the image to the right, that will increase our aerodynamic drag to reduce our apogee through an increase in overall launch vehicle cross-sectional area. At a system level, our design consists of radial flaps that are driven by a servo motor mechanism. We utilize a integrated PCB that utilizes sensors for both data collection and a microprocessor to drive our software. Our software utilizes onboard computing of a custom dynamics model, which allows us to solve for actuation systems through a closed loop feedback controller in real time throughout flight. So our air brake system seen here and also shown actuating the video there consists of 2 bays, an electronics bay at the top and a mechanism bay shown in the middle. These 2 bays isolate the 2 systems from each other, allowing for assembly of the 2 systems together. Our mechanism consists of a pair of inline slider crank mechanisms. This system consists of a cam drive in the middle, connecting with 2 connecting rods on the ends. This ensures that our system actuates the flaps at the same distance from the exterior of the airframes, reducing any chances of inducing a pitching moment on the launch vehicle. The system is driven by a high torque servo motor, which has a factor of safety of 1.95 of its stall torque, which is derived from maximum actuation of the air brake system along with maximum vertical velocity of our launch vehicle. The system leads to an overall increase in launch vehicle cross-sectional area of 21%, driving our increase in aerodynamic drag. The electrical design of the system consists of an integrated PCB shown to the right. This system utilizes both a barometric pressure sensor and an inertial measurement unit, which allow us to calculate the state of the launch vehicle throughout flight, namely our altitude, velocity, and pitch orientation. We utilize a Raspberry Pi 4 Model B microprocessor. This was chosen for both of its computational capabilities and its open source libraries that allow us to utilize seamless integration with our sensors. For the power supply, we use three 18650 lithium-ion cells, which provide us with 12 volts of power. Our sensors run off 3.3 volts, microprocessor 5 volts, and our servo motor 7.4 volts. Thus, our system has 3 linear voltage regulators that downregulate the 12 volts into the 3 respective power lines. And then finally, our PCB also utilizes a low voltage cutoff circuit. This ensures that if the power system drains below 9 volts, no more current will be provided to the PCB, ensuring that we do not drain our lithium-ion cells below their rated voltage. As mentioned before, our system utilizes onboard computing to solve a custom dynamics model. This dynamics model is a three degree of freedom system, only considering in-plane motion, and the free body diagram shown there in the middle. Assuming a 0 angle of attack during the coasting ascent phase of flight, we only have the aerodynamic drag and weight forces with their lines of actions going through the center of gravity of the launch vehicle. This allows us to derive our equations of motion for both the downrange and the vertical state of the launch vehicle. Our dynamics model can then generate a flight profile, which is shown in the image to the top right, plotting the altitude of both our dynamics model and an open rocket simulation for similar initial conditions. You can see that our dynamics model predicts a lower apogee than the open rocket simulation. This is because, as George mentioned earlier, our modular aft utilizes fin brackets, which have a complex geometry that cannot be modeled easily in open rocket. Thus, our dynamics model has a overall higher aerodynamic drag on the launch vehicle. Finally, we use this dynamics model to then drive the design of our controller, which is a proportional integral closed-loop feedback controller. The main design considerations for this controller was both to minimize overshoot and steady-state error. Since our system is an under-actuated system, we are only able to reduce the apogee of our launch vehicle. However, if we overshoot, we have no way of getting that altitude back. And then we also include an integral term to eliminate any steady-state error, allowing us to refine our final apogee. The air brake system software can be broken up into 6 states that chronologically follow the flight profile of the launch vehicle. Through an external arming switch that we utilize on the air brake, we can arm the arm the air brake system on the launch pad. This then enters the software into the pad state, which will actuate the air brake system to full extension and then back to its home position. This provides the arming team with a visual cue that the system has been powered on and is operating nominally. Then we switch over into our arm state. In the arm state, we run a ground calibration software that will calculate our ground pressure and ground temperature that is later utilized to calculate our altitude throughout flight. And then we also run our launch detection algorithm. This launch detection algorithm, once the motor has fired for our launch vehicle, our launch detection algorithm will pass and transition us into our launch detected state. During the launch detected state, we run a motor burn timer plus a 1/4 second delay. This ensures that we do not actuate our system while we are under powered flight. Throughout this time, we are also calculating the state of the launch vehicle through our sensors, namely the altitude, vertical and downrange velocity, and the pitch orientation of our system. Once that motor burn timer has completed, we switch over to the actuation state, which is the coasting ascent phase of flight and also the area in which we actuate our air brake. During this time, we take the state of the launch vehicle, pass that into our dynamics model, solve for a predicted apogee at each loop of the controller, and solve for air brake actuation signals in real time. Finally, once we reach apogee, we transition into our descent state, which is simply us logging all of our sensor data throughout descent. And then upon landing, we log all of our data to a CSV file and end the execution of our software.
Hello, everyone. My name is Jade Wagner, and I'm the flight dynamics lead for this year, which focuses on motor selection and full flight simulation. The motor selected was chosen to optimize 3 competition requirements: the margin of stability off the rail, the thrust-weight ratio, and the velocity off the rail. The margin of stability off the rail and the thrust-weight ratio meet competition requirements, and the velocity off the rail was below competition requirements, and therefore a test flight was done to prove flight safety. The motor chosen was chosen to have an apogee that was between 10,500 feet and 11,000 feet, as the simulation was with the air brake not deployed, and the air brake would decrease apogee by 500 to 1,000 feet. Therefore, an N motor was selected. Through the design process, as the launch vehicle was updated, the final motor selection was the Aerotech N3300 RPS, with a total impulse of 14,041 newton seconds, an average thrust of 3,168 newtons, and a thrust duration of 4.4 seconds. The motor will be housed using all Aerotech motor hardware, and an Rocket Pi visual graphic of our COTS motor is shown at the top, and its thrust curve is shown at the bottom. The flight profile was done using 3 different simulations: OpenRocket, RasAero, and Rocket Pi. OpenRocket was used for its full flight profile and its ease in updating individual components. However, OpenRocket overestimates drag when coming close to Mach numbers of about 1. So RasAero was introduced as it uses experimental data in its calculations and has the ability to add protuberances to the launch vehicle, which was added to account for the fin brackets on the modular aft section. However, RasAero does not account for an air brake in its simulation, and therefore a Rocket Pi simulation was introduced to account for air brake actuation during flight. Furthermore, Rocket Pi has the ability to introduce a drag curve using CFD data, which was introduced as an initiative for future years in the Spaceport competition. As mentioned before, a flight test was done, and the apogee was measured in 3 different ways: the air brake flight computer, the tele-GPS, and the SRAD flight computer, as the COTS altimeter was damaged due to water damage in flight. And therefore, the measured value is an average of these 3, being 10,424 feet. This can be compared to the 3 simulations used, and RasAero was proven to be the most accurate for apogee calculation. And therefore, it will be used for the majority of the calculations of the launch vehicle for the competition. The final flight results can be seen in the table at the bottom. It can be noted that the launch conditions are for Truth or Consequences, New Mexico, with a wind of 20 miles per hour and a temperature of 95 degrees. This is an average of the 2023 Spaceport competition that same day. And it can be shown in the table that the stability off the rail is above the competition requirement of 1.5, as it is 1.83 calibers, and the thrust weight ratio exceeds the competition requirements of 5:1 with a 9:1 ratio, and the velocity off the rod is 80.4 feet per second. Also note that the stability off the rail, and thrust weight ratio was calculated in OpenRocket. The max velocity, max acceleration, max Mach number, velocity off the rod, and apogee was calculated using RasAero. The mass of the rocket without the motor is 66.1 pounds, and with the motor is 93.1 pounds.
Hello, my name is Lisa Stutsenko, and I am the Payload Integration Engineer, and I will give a brief introduction to our payload for this year. So our payload for this year is a 4U CubeSat chase camera that will be deployed from the rocket at around 1,250 feet. So as Jacob mentioned earlier, the payload will be deployed via a cold CO2 ejection to prevent damage to any of the electronics and other critical components in the payload, and also a sabot will be used for the safe deployment of the payload. The mission for this year's payload is to track and to take a video of the launch vehicle descending upon the main parachute by automatically moving a camera that is at the bottom of the payload. And this video will be live streamed to a ground station. In addition to the deployed payload, there will be a separate data transmission unit within the nose cone, and this data transmission unit will start transmitting the rocket's positional and altitude data to the payload. And with this positional and altitude data, the
payload can orient itself to take a video of the descending rocket by using the flywheel, the steel flywheel that is inside the payload, to rotate the payload towards the rocket, towards the launch vehicle along the roll axis, and also using a servo to pitch the camera along for vertical tracking of the launch vehicle. In addition, there are various sensors in the payload, such as an IMU, a barometer, and a GPS, and this data is then logged to a micro SD card.
Hello, my name is Gavin Spur. I am the payload mechanical lead for this year. To begin, I would like to walk you through the payload modules. As you can see in the render and in the actual payload next to me, at the very top, we have the parachute box. Below that, we have the battery module. Below that, we have the PCB stack up. And then finally, below that, we have the flywheel module. And at the very, very bottom, we have the camera module used for tracking the rocket. As far as the overall structure of the payload goes, it consists of a top plate, 2 middle plates, 4 support beams, and a bottom plate. These top plate, middle plates, and support beams are all made out of aluminum for their desired strengths, as well as the ease of manufacturability. They provided us a balance between intricate design as well as structural components. The bottom plate is made out of polycarbonate to ensure that the camera can see through the bottom and see our rocket during descent. Next. To ensure the structural safety of the beams, we conducted analysis on the expected load. As you can see on the left, the expected load from the plates is acted upon the beam. On the right, we have the stress and strain results. As you can see, there are no troubling readings. Therefore, we deem the beams to be structurally safe for the duration of our flight. Now going into the modules, at the very, very top, we have the parachute box. This module consists of a PET-G parachute box, a PET-G GPS holder, a half 13 eye bolt made of steel. The parachute box and GPS holder were made out of PET-G for weight constraints, as well as the fact that the GPS housed in them may not touch metal to ensure that the readings are transmitted to us on the ground station. To talk about the GPS, the functional components are an egg finder GPS and a 5-foot Rocketman elliptical parachute that is used for recovery and attaches to the eye bolt. Right below this parachute box, we have the battery module. This module consists of a battery holder made of PET-G, a battery buffer made of PET-G, and 8 18650 lithium ion cells. These are both made out of PET-G for the ease of, as you can see, the design is very intricate to allow wires to pass out. Therefore, 3D printing was deemed to be the best way to manufacture this very intricate and complex part. As you can see with those holes, the wires are able to seamlessly exit, and there's no issue with the battery getting power to the rest of our systems. Finally, or not finally, next below the battery module is our actual PCB stack up. From an electronic standpoint, our electronics lead Dylan will get more specific with the components of each board later. However, from a mechanical standpoint, it consists of 24 PET-G spacers and M3 by 0.6 standoffs. The purpose of the spacers is to ensure that the aluminum standoffs do not short circuit the boards or cause any issues with the electronics. This ensures our PCB signals reach all of our functional components throughout the rest of the systems used to track the rocket. Below the PCB, we have the flywheel module. This consists of the flywheel, the bearing mount, a 624 2Z ball bearing, a motor mount support, and a motor mount. This entire system is used to support the flywheel and a brushless motor that can spin up to 6,700 RPM and has an impulse of 0.74 Newton seconds. Our flywheel was CNC'd and is made out of steel because of the weight properties. To reach the needed inertial values to actually rotate this payload whenever it is descending, the weight of the flywheel is very needed. Therefore, nothing like aluminum or any other material could be used. Because of its weight, however, this system is made of 4 other parts, as the bearing mount, the ball bearing, motor mount support, and the motor mount itself. The bearing mount and the ball bearing are made to ensure that the shaft of the motor does not deflect during descent due to any radial forces the flywheel may exert. The motor mount support is then there and is epoxied into our ABS motor mount. This is to ensure that the ABS plastic, which would have otherwise been carrying most of the load, does not carry most of the load. Instead, the epoxy and aluminum take on most of the load, therefore increasing our chance of no failure or anything wrong with this module due to the weight of the flywheel. Finally, at the very bottom, we have the main goal of the payload, the camera module. This camera module consists of a servo bracket made of PETG, a camera buffer, and a camera holder. The functional components of this module are a Mista FPV camera and an RC servo RDS 3218. The servo has a 270-degree range of motion, allowing for adequate pitch correction whenever we are trying to track the rocket during descent. This servo bracket and camera holder are made custom because the camera does not fit perfectly with our servo. So to ensure seamless integration, a custom bracket and holder were made of PETG for their intricacy of the mold itself, having to fit the exact geometry of the camera.
Hey, I'm Dylan Orodowski. I'm the payload electronics lead. Here we have a block diagram of our electronics system. As Lisa mentioned before, we have three major subsystems. We have a data transmission unit, which stays fixed within the rocket. We have a CubeSat, and we have our ground station. Our data transmission unit consists of two PCBs, both SRAD, this being a primary processor PCB and a coprocessor PCB. The CubeSat uses an identical copy of those two PCBs, as well as a brushless motor driver PCB. In addition to our SRAD PCBs, we have an egg finder GPS. This is used only for recovery purposes of the payload. And we have a camera and VTX system to transmit our video feed. Our ground station is solely for displaying this video feed. So we have an RCA video receiver, which we then convert to HDMI and send to a video capture card to record the video, as well as an HDMI output to display it in real time. We have, as I mentioned, three SRAD PCBs, the first of which is a primary processor PCB. This contains a STM32 digital signal processor operating at 550 megahertz, as well as a 9-axis inertial measurement unit and a barometer, as well as an SD card reader for data logging. Our coprocessor PCB contains an AT-Mega, an XB radio transceiver, and a GPS. The reason we're using two different processor PCBs is so that we can get the computational throughput of the STM operating at 550 megahertz, while still being able to flash Arduino firmware onto our coprocessor, giving us access to existing firmware libraries. This gives us both computational throughput and ease of software development. Finally, we have our brushless motor driver PCB. This contains three H-bridge motor driver circuits, as well as a low voltage cutoff to cut power to our battery system at 9 volts. For telemetry, our CubeSat has three transmitters. We have one 250 milliwatt S3 Pro transceiver. This is operating on the 900 megahertz band. We have a KCO2 600 milliwatt VTX transmitter. This is operating on the 5.8 gigahertz band, and this is sending our video feed. And finally, we have an egg finder GPS transmitter, also on the 900 megahertz band, that is being used to transmit the CubeSat's location back to our ground receiver. On the data transmission unit, we have one XB Pro transmitter that is transmitting the launch vehicle's location to our CubeSat for tracking purposes. For our camera, we are transmitting at a 600 TVL quality. This corresponds to 768 by 494 pixels. Our ground station then upsamples this and converts it to 1080p, 60 FPS HDMI output. For our power system, we are using 18650 lithium-ion cells on our CubeSat. Each cell has a current capacity of 3,500 milliamp hours with an 8 amp current output rating, and these are configured into a 6S and 2S pack. On the data transmission unit, we have a single 2S pack of 18650 lithium-ion cells. For our battery durations, we are expecting 9 hours on our CubeSat 2S pack, 29 hours on our 6S pack, assuming motor is idle, which it will be for the duration of flight, and 10 hours on our data transmission unit.
Hi, everyone. I'm Jordan Hayden, the payload software lead, and I'll be talking about how the mechanical aspect and the electrical aspect were integrated in our software code. So for this project, we wrote 2 codes, one for the primary board and one for the coprocessor. The primary board, we used the STM32 Cube IDE library, and we wrote to the STM32 8725 VGT3 processor. So this code actually comprises of all of the code for the IMU integration, the barometer to get the pressure reading, SD card for data logging, the servo motor for tracking the vertical pitch of the rocket, as well as the flywheel to control its orientation. We did several tests. However, the main 2 that we did were for the sensor data logging. We did that for the IMU, where we collected the acceleration reading, and that can be seen in the top right-hand corner picture of the screen, as well as we did some data logging tests to test if the data is successfully being stored to the SD card. Additionally, we wrote to the Arduino for the coprocessor, and this code primarily just gets the GPS reading as well as the XB reading from the coprocessor of the rocket and transmits that to the payload so that we can do further data testing. We use the XCTU software to do XB communication and range testing, and this was successful. So for the general flow chart overview of everything, so upon power up, a red LED will indicate that, hey, power is going to the circuit. And before data logging begins, the payload will be in an idling stage. So at this stage, we will get the reading from the IMU and the pressure, but we will not be storing this to the SD card. This will not happen until when the payload is ejected at 1250 feet, right? And this is detected by the IMU reading as well as the pressure reading from the barometer. When this is detected, the GPS coordinates from the rocket will be sent to the payload, and at that point, everything will happen in a control feedback loop system, and the servo motor will do a vertical tracking of the rocket as well as the flywheel will control its orientation to ensure that the payload is successfully tracking the vertical descent of the rocket. Additionally, we will be doing some live streaming, and this will be sent to the ground station, and this was mentioned by Dylan a while ago. The control loop system will continue until when the payload has landed, and at this point, the data logging will stop and everything will end, and this will indicate that our mission was successful.
Hello again. I'm going to now be talking about the payload recovery and retention. As shown in the table here, we selected a 5-foot Rocketman elliptical parachute because of its coefficient of drag of 1.6. This gives us a descent rate of 16.5 feet per second. This is important because it allows the bottom of our payload to be able to be above the rocket during descent, as the rocket descends at 19.2 feet per second. When it comes to the actual retention retention of the payload, we utilize a 3D printed sabot. The first thing I will show you is our old tested sabot. It is made out of PETG, contains 4 sides, a bottom ring, 4 Kevlar shock cords, and 2 D-links. It's a little bit messy because of the test flight. However, as you can see, these sides that are dangling are held together by the shock cords that are tethered by a D-link at the very top. This ensures that during ejection, these sides do not actually release from the rocket itself and fall into free space. Obviously, the clean new version was made, and this has the same functionality. Just for a better look at our bottom ring, it is a 3D printed ring with pegs. These pegs house the 4 sides shown in the picture. When it comes to the actual payload integration to the sabot, as you can see in the picture, it is placed upside down with the parachute facing in. This is due to during the test flight, we suspect the eye bolt sheared. That will be talked about a little bit later. However, placing it in this way ensures that the entire body of the payload will slide out of the sabot and not the parachute first, reducing the risk of any failure with the recovery and retention. As you can see, the sabot is in a cylindrical shape. This mocks the airframe. The diameter of the airframe is 25 thou less in diameter to ensure for sliding. And it is placed into the forward airframe, just slid in there with D-links connecting it to the front cone and to the CO2 ejection system to allow it to be shot out and successfully protect our payload during ascent.
So I will go over a brief concept of operations for our payload. So initially in the ground state, the payload is powered on, assembled and integrated, and the powering on is confirmed through a blinking LED on one of the PCBs. The sensors are then continuously checking for launch, and the payload is in an idle state. During vehicle launch, the sensors detect launch and they start logging the data to an SD card. During drogue descent, the payload is still waiting for ejection at 1,250 feet. During payload deployment, the payload deploys and the servo and the flywheel are activated. At this point, the data transmission unit in the nose cone is transmitting the rocket's positional and altitude data to the payload. During payload descent, the payload is completing its mission. It is transmitting a live stream of the descent of the rocket upon the main parachute to the ground station. Additionally, the servo and flywheel are also allowing for the vertical tracking and orientation of the payload for this mission. During payload landing, the sensors, data logging, flywheel, and servo are all disabled, and the payload completes its mission.
Hello again. So as our leads have hinted so far, we've had a fully integrated test flight before this presentation, and our chief engineer will get into some of our findings later on. However, before the test flight, we had some ground testing done to the vehicle where we tested the ejection of the parachutes as well as the payload, where we integrated the launch vehicle fully and put 2.6 grams of black powder into the drogue airframe and then ignited the charge to see if the parachute would deploy successfully, which was successful. However, we'll be repeating this test before the competition flight due to the fact that we've changed our drogue parachute since the test flight. And we've also done a payload ejection test with the CO2 system, where we use a 25-gram CO2 canister. This resulted in the nose cone separating successfully and the payload deploying not fully, but we thought this was fine before the test flight. However, after our findings during the test flight, we wanted to up the CO2 canister charges to 33 grams, and we'll be testing this again before the competition flight as well. Also, the main parachute deployment test was done with 3.7 grams of black powder, and this also was successful, where we had successful separation and parachute deployment. However, we'll be repeating this test as well due to the fact that we've changed our main airframe, which was severely zippered during the test flight.
All right, hello. So to kind of wrap things up, I am going to talk about our test flight, just kind of overall generally. So we've hinted at it a lot. We did do a fully integrated test flight just around a month ago on March 30th. I'll talk through sort of what went well, what didn't go well, and what we've done since then. We saw a fully successful ascent of the rocket. The modular aft system worked as was simulated. We saw no failures there. No failures to our aero body during ascent either. Our air brake system proved to data log successfully and overall operated successfully. There was some minor issues with the software at the time, so it didn't actuate fully, hence our apogee still being over 10,000 feet, but overall was successful, and we're able to fix that, and we'll still be aiming for that higher apogee that the air brake will bring down during the competition flight. We started to run into some issues during our descent. We did see successful drogue deployment. Payload deployment, however, we saw the payload section deploy, but quickly saw that our payload had separated from its parachute, and it ended up descending at terminal velocity and was not able to be recovered. However, as you can see, we have it here because we did rebuild it in the month following the test flight. So we're still going to be flying the same mission that we originally planned. We did make some tweaks to it. However, Gavin talked about reorienting it in the rocket. That's one thing that we're doing differently so that the parachute can't catch air before the entire payload has come out and rip against the side of the airframe or anything else. We're not exactly sure what happened to it, but we suspect that that could be an option. We suspect the eye bolt could have sheared, and so we've upped the size of the eye bolt. And then finally, another option could be that the top plate itself of the payload was ripped out, and so we went for a thicker top plate and some bigger screws there as well. Other issues that we ran into following that, you can see the picture, our main airframe zippered terribly under our main parachute deployment. Reasons that we suspect that could be, Jacob talked about our high deployment velocity for the main parachute, as well as the fact that we originally did have this airframe made out of our SRAD carbon fiber airframes, which are very thin. And so since then, we have lowered our deployment velocity of the main parachute, and we've also changed this airframe to be a fiberglass airframe now. And in the future, we're going to investigate for our team making our SRAD airframes thicker to accommodate these high loads during deployment. We also tore our main parachute protector, and this is something that's happened to us a couple years in a row. And so we're going to be buying we have bought a stronger parachute protector that we plan to reinforce ourselves, just sewing it by hand. And then rather than knotting those off, we're going to attach them with a D-link to hopefully keep those from ripping out. The last thing is Jade referenced that we had some water damage. We are in Florida. We did get unlucky and we happened to land in a swamp. We were able to recover the entire project other than the payload, but we did lose a lot of our PCB boards and electronics. And so we are currently in the process of resoldering our boards. And we did make some design changes to our altimeters based on what the team had in inventory and what we were able to get to replace those. Very last thing is they also reference the steel bulkheads. That is something that we implemented as an interchangeability component due to the fact that the altitude and weather is so different in Florida versus New Mexico. It allows us to fly to 10,000 feet in Florida and in New Mexico. So as the very last thing to wrap it up before we go to questions, I'm going to quickly walk through again just our concept of operations for the whole project. We have our full launch vehicle, which lifts off with an N3300 Aerotech motor. During our coasting stage of ascent, our air brake system will actuate, slowing the rocket to hit a 10,000 foot apogee, where our drogue deploys. It'll descend under drogue until 1,250 feet, at which point our chase cam payload will deploy and begin to descend under its parachute. At 1,000 feet, the main parachute will deploy, and these two will descend simultaneously, the payload having a slightly slower descent rate, keeping it above the rocket such that it can film and perform its mission. And then we'll see the vehicle touch down, and shortly thereafter, the payload touch down. So thank you all very much for listening to us talk for this past hour and share our project. I'm happy now to kind of field questions to our leads about the project. Our camera is also, we can take it and move it around and show you some things up close if you'd like to see. So we're happy to do that as well. We just left it up there for the presentation, but we can take it down and move it around to show anything that we have on the table here.
All right, fantastic. First of all, thank you so much for such a detailed and well thought out presentation. Even though it took an hour, there was a lot of information to convey. I do have some questions, which I wasn't able to catch in the presentation itself. What are the shoulder lengths for the parts of the rocket that will come apart?
So the separating joints are all 6 inches.
Okay, that is perfect. All right. Let's see. Is the team number painted on the rocket?
It is not painted on. We didn't paint it for the test flight because we figured it would get dirty, but it will be painted on the rocket.
Okay. Good to know. Be painted, and yeah, all rockets get dirty once you wash them, so that's understandable. All right. Let's see. Do all the batteries used meet with the newer battery requirements?
Yes.
Okay, good.
They're all 18650s in metallic cylindrical containers.
And that's for all the electronics?
Yes, all of payload electronics as well as the air brake. Jacob, and our recovery uses 9 volts.
Also here, since the payload separates your team number and the frequencies will have to be marked on that as well.
Correct, yes.
Okay, good. All right. What is the motor mount made out of?
For the payload?
For the payload, or are you referring to the motor mounts
motor.
of the modular aft? Yeah, so the whole modular aft system that George talked about, the thrust plate is all 6061 aluminum. The actual motor retainer itself is a off-the-shelf Aeropack motor retainer.
Oh, so you just slide the motor into that structure. There's no like separate tube.
Correct. There's no like motor tube. We slide the casing directly in.
Let's see. What's the current fin flutter velocity?
Jade can go ahead and answer this one.
The current fin flutter velocity is about 2,500 feet per second, which is way above the requirement of 50% over the max velocity of the rocket.
Yeah, that's probably closer to 100% over the
Yeah.
maximum velocity.
Yeah, exactly.
Let's see, actually, that's that. What are you using for rail buttons?
For rail buttons, we're also using off the shelf the Delrin Delrin rail buttons, airfoil ones, and they're reinforced through the airframe with T-nuts.
Okay. All right. So, all right. My other questions. What type of infill and pattern are you using for your 3D printed parts?
We're using we're using typically it's 20, at least for the payload, 25 to 30%, depends on what we deem needs to be a little bit stronger. For example, the sabot was all printed at 30% infill with, I believe it's hexagonal. Yeah, it was hexagonal. Yeah, with hexagonal pattern. And they were all printed so that they'd be strong in the way that they'd take on load as well. But for the majority, it's from the range of 25 to 30%.
Let's see. Do I have any other questions? Okay. Let's see. I'd definitely say you are not exactly ready, but well on your way to be ready. Since you have a couple things left to complete, but you do have about 7 weeks.
Correct. Yeah. Yeah, we're anticipating to finish up our soldering for our boards here in the next like few weeks, and then the re-ejection testing of our launch vehicle with some of the alterations we made is our last main test for the vehicle, and we're planning on doing that in the next week or so as well.
Sounds good. All right. I have a couple stuff which I have here to pass along, some of which you probably already know, particularly those of you who attended last year. You are required to provide your own food and water during the event. Water, definitely, yes. It will get hot. You'll also need to transport everything. Since you're in Florida, we don't have to worry about any international stuff, which is always more of a pain. Yeah, so you don't have to deal with shipping unless you want to ship stuff.
No, we're gonna drive it.
Okay. All right. For those of you who haven't been to Spaceport before, there is a border check in between Las Cruces and the launch site. If anyone on your team is not from the US, you will want to carry ID. Even if you are from the US, you might as well carry it in anyway. Usually it's just a short stop if you are stopped. This year, you do not need to bring tents or tables. We are providing those, which is super nice. I wish when I was a participant that was the case. We didn't have a table or chairs. Yeah.
Is it in the dirt?
What? We had a
We're
tarp.
just in the dirt. Oh, a tarp. Oh yeah. My bad.
Yeah, standards were a bit lower back before 2019. Yeah, so temperatures can get very hot this year. So the 115, I think our hottest temperature last year was 106. So dress appropriately for those type of temperatures. Black is not a good color. Sadly, for your very fancy team shirts.
We got other options.
Okay. Let's see. Yeah, travel arrangements. You're driving, so that's good. We don't need to worry about visas. Do you have a hotel already selected?
Yes.
Okay. I don't think I really need to ask where. All right. Does everyone who is planning to go on to the pads have appropriate like certification, well, not certifications, but memberships?
Yes, the whole team actually has a Triple E membership.
Yeah. And you have let's see, does any of your stuff require a ham license?
We do, and Con and Jose are both ham license certified.
Fantastic. All right, and you definitely have an FOR, that's Jimmy there. All right. Just as a final note, I don't think I need to worry about it because your rocket is already painted, but don't do any painting at the hotel. They won't like it. And don't assemble your motor there either.
Okay.
And finally, the only other thing I have left is to let you know, make smart choices, which you have based on your presentation. Be safe, have fun, and don't do anything stupid.
Understood. Thank you.
You're very welcome. Now, do any of you have any questions for me?
Anybody have any
before we
questions?
end?
Especially people who haven't gone to Spaceport before. Maya, our project manager, was asking, we know there's a couple of other forms and things that will go out about the recovery training and the frequency allocations and things like that. Do we know when we might expect to start seeing those things roll out?
I would say shortly. The frequency allocation, that's up to DaVinci. They're technically separate from Ezra. And that's as far as I know. You are not the only team to ask that question. Of the teams that I'm reviewing, I believe I have had 3 so far ask that question. Yeah, so the other training, yeah, that should also be released within probably the next several weeks, hopefully.
Awesome. Thank you. I don't think we have any other questions.
All right. So this recording, do you know the email address to send it to?
Yeah, it's the general email address, right? Or we
Yep.
also have the document that we the document for this to pull up the email.
Fantastic. So you'll just need to send that to that email address by the 19th. So you have plenty of time. And just in case anything happens to your recording, I have one as well.
Okay. Fantastic. Thank you.
You're very welcome. Congratulations again, and I will see you guys at the competition.
Awesome. Thank you.
Thank you.
Thank you, Jimmy. Thank
Good
you for
work.
coming.